All right, we are now recording. So as always, please type hello into the chat box or hi or here or something like that. Otherwise, you won't get credit for being here. Okay, good. That's the way to go. Keep on going there. Okay. Now, before I start into the new material, let's talk about last night's homework, at least if you have any questions about it. If not, we can just skip right on. So do you have any questions about last night's homework? Not hearing anything? Not seeing anything. All right, well, let me tell you a little bit about my feedback from what I saw. I graded everything that had been turned in as of last night, and I've graded some of the stuff that was turned in this morning, but not all of it. Okay, so I think everybody pretty well figured out how it works. So the data that you see right here, the Y1 data, that is the protractor data. And the error bars, now this was a little tricky. The error bars here go with the protractor data. I had a couple of you who turned on the sextant data by clicking on Y2, which was the right thing to do. But you kept the error bars in place. Those are the error bars for the protractor data. The error bars for the sextant data are these right here. And when you click on them, it's kind of hard to see because the error bars are so incredibly small. They're actually within those dots there. If I toggle on and off and you look closely at the dots, you can see them. And if you zoom in, you can see they are in fact there. All right. So I think most of you got most of the homework pretty good. Let's talk, whoops, I always do that. I move the mouse without clicking first and then it does that. Okay, let's talk about a little bit about the sextant data versus the protractor data. All right, so the sextant data, let's turn that off. And there's the protractor data. Oh, let's see, it looks like, well, I still got the error bars on for the sextant data. Okay, good. All right, let's talk a little bit about precision versus accuracy, because that's going to be part of tonight's homework is precision versus accuracy. So let's make sure that we understand what is precision, how is it similar to but different from accuracy, and let's use the protractor and the sextant as our examples. Remember when I said that we measure a star with the protractor, what's the closest we can hope to get? Plus or minus, how much did we say it was for a protractor? Was it plus or minus 1/100th of a degree? Was it plus or minus 1/10 of a degree? What was it? Plus
I
or
think it
minus?
was either a degree or a tenth of a degree, though probably a degree.
Yeah, 1 degree is right. And to be honest, that's even pushing it. Um, I think most of you'd be lucky if you can get plus or minus 2 degrees, but let's be generous. So then what we say is that the best possible precision with a protractor is 1 degree. So if we were to measure a star, like let's say we measure Polaris from Salt Lake City using the protractor, if we report the altitude is 40.75, we are smoking something. If we used a protractor, there is no way that we can get that level of accuracy. Let's talk about that, in fact, because again, this relates very directly to what we're going to do in tonight's homework. Okay, so if I report the answer as 40.75, what that means is that I am confident that the real answer is somewhere between 40.745 and 40.755. That's what it means if I report it to that level of precision. And now some of you are going to say, well, Mr. Hendricks, on the left side, it should be less than or equal to. Because if it really was 40.75, if we rounded that off, we would round that up, not down. Okay, so what I really should have said is less than 40.754999 repeating. But the way I'm going to handle that is I'm just going to say less than but not equal to, and that way I can get away with writing it this much easier way. Okay. All right, so there is no way I can get that level of precision with a protractor. But if I use my sextant, then it is reasonable that I could, because a sextant does have a precision of plus or minus 1/100th of a degree. So it is reasonable for me to say that. Okay, so that's precision. Precision is a measure of how much uncertainty there is in the number. Now, what about accuracy? Okay, which of these two tools do you think is more accurate? The protractor or the sextant? I want you to type something into the chat box there. Which tool do you think is more accurate? The protractor or the sextant? Okay. All right. So everybody seems to agree that's the sextant. Is there anybody out here who thinks that the sextant might possibly not be more accurate? Anybody willing to unmute yourself and tell me whether or not it's possible that although the sextant is clearly more precise, it might not be more accurate?
Well, from my understanding of accuracy, which is, say you're aiming at a point, accuracy would be how close you aim, like how close your target hits to where you're aiming. Or, I mean, how close your aim is to your target. Well, precision is how close a bubble of uncertainty that is from where you hit.
Okay, very good. That is the way that most people teach it. And in fact, I'm pretty sure that Mr. Miller uses that same analogy. So let's take that and look at it. So if we have a dartboard, so pretend that these are circles, even though they're pretty terrible. All right, so in the middle there, that's the bullseye that we're trying to hit. All right, let's suppose that we got somebody who's throwing red darts. And so one red dart hits right there, another red dart hits there, another red dart hits there, and another red dart hits there. All right, now somebody else steps up and they're going to throw blue darts. So one blue dart is there, the other blue dart is there, another one is over here, another one is over here. All right, so who is more accurate? Well, no, let's start with precision. Let's start with precision. All right, which one of those guys has better precision? The red one or the blue one? I want everybody to type in
the red darts.
Okay, so I hear one vote for red. How about everybody else? Okay, so everybody's agreeing that the red darts are more precise because they're more repeatable. But what about the accuracy? Well, okay, it gets a little bit iffy here. Some of those blue darts, where I put them, you could maybe argue that they're not so good. So how about if I do it a little differently? Let's try the blue darts again. So, okay, now still the blue darts are less precise. Okay, so the red darts are still more precise, but the blue darts are closer to the real answer. So the blue dots have better accuracy, even though they have worse precision. So can anybody think of a way where my sextant, which clearly has better precision, might not have better accuracy? Is there a way that could happen? I propose there is. Nobody wants to speak?
I'm trying to think, because if it has better accuracy.
I'll tell you what, to save time, okay, what if I set my sextant on the chair, and then when I'm not thinking, I'm not looking, I sit down, and so I sit on my sextant. So there are parts in here. Now, you guys don't know how sextants work, so it's understandable, but there are mirrors here that need to be adjusted right. There's an arm here that needs to be adjusted right. So if I were to sit on my sextant and bend the arm, or maybe push the mirror out of alignment, okay, if I don't notice that, I could sit here and I can go around measuring stars, and I could get answers that are incredibly precise, but they will be horribly inaccurate because things are bent there, right? So it's entirely possible that you can have a tool that is much more precise than another tool and yet is less accurate. Now, if we were in class, this is one of the things that I love to do with students. I love to give them tools to measure things that I have purposely messed up the calibration on. And so here they're measuring stuff and they're getting great repeatable results. And they have no idea that their results are way the heck off because I have purposely messed up the calibration on them. If we were in class in person, I would do that to you too. But unfortunately for me, fortunately for you, we can't do that. So you'll just have to use your imagination. All right, so accuracy versus precision, those are two things that we're definitely going to be talking a lot about for the rest of the year. Well, I'm going to assume that you know them for the rest of the year. And in tonight's homework, you definitely are going to have to pay attention to them. Okay, let's see, what else is there in tonight's homework here? How about, let's go into my little presentation here. All right, so in your homework tonight, we're going to be working out of chapter 1 from the textbook. If you haven't yet picked up a textbook, you better go get one. Stop off at Ames, talk to the people in the front office. They'll get you a textbook. You're definitely going to need it. We're going to be using it heavily. All right, let's start off with a question here. I want you guys to type in the chat box what you think the answer is here. What is the answer to this question as worded? All right, I see a lot of people saying 8. A lot of people are saying 18, but Taituan is saying LOL. How come you're saying that, Taituan? Why are you suspicious that 18 might be the wrong answer? Because you are correct in being suspicious that way. You guys see what Taituan typed into the box there? He says, "'Cause you're Hendrix." That's good for you, Taituan. You're gonna go very far in this world. You're going very far in this class anyway. Okay, yeah. So if I was a math teacher, if I asked you what is 6 times 3, okay, a math teacher deals in absolute numbers. So when a math teacher talks about the number 6, they are talking about the mathematical concept of a number that is exactly 6. And so when they say, what is 6 times 3, then yeah, I agree. The answer is 18. But this is not a math class. This is a physics class. And we are going to be dealing with numbers where they are not necessarily the mathematical concept that is exactly equal to 6. We're going to be dealing with measured values in this class. So rather than asking what is 6 times 3, how about, let me ask it differently. I'm going to ask, what is the area of this rectangle? Okay. And you can see here by looking at the rulers that I put on here, you can see that the width here, let's see, I forgot to turn on, okay. All right, so oh, actually it was on, we just didn't see it because the color, let me change color. Okay, and try this again. All right, so our width here, is it exactly 6 or is it approximately 6? Well, the answer is it's approximately 6. Whoever did the measurement here, they might call it 6 because it's really close to 6, but it might not be exactly 6. And then same with the height. Okay, our height here looks like it's 3, so we might call it 3, but is it exactly 3 or is it more approximately 3? So if I ask you what is the area of the rectangle, well, if somebody measures the width and they call it 6, and somebody measures the height and they call it 3, and so you're going to say, well, the area is the width times the height, and it's 6 times 3, and so you're going to say 18, and I'm going to say no, because this 6 now is not exactly 6. It's a measured value, which is approximately 6, and this height is not exactly 3. It's approximately 3. So if we answer 18, that is wrong. And the reason it's wrong is because if you say the answer is 18, what that means is you are confident that the area is somewhere between 17.5 and 18.5. Hang on a sec. I got some windows that you guys can't. I've got some windows on my screen that you guys can't see, and those windows are getting in the way and messing me up. Okay. So if you report the answer is 18, this is what that means. But do we in fact know the area that accurately? No, not on your life. We do not. Okay. Let's see how accurately we actually know the area. So if we reported the answer for the width as 6, what that means is that the width could actually be anywhere between 5.5 and 6.5. Same thing with the height. If we report the height as 3, that means the actual number could be anywhere between 2.5 and 3.5. All right. So let's see what the real range of uncertainty is on the area. Let's take the lowest number for the width multiplied by the lowest number of the height, and let's see what that works out to be. So I'm going to get out my calculator. I recommend you guys do the same. So 5.5 times 2.5. So the area could be actually as low as 13.75. Okay. And then let's do the same thing for the largest range. So the width could possibly be as large as 6.5, and the height could actually be as large as 3.5. So let's take 6.5 times 3.5. My calculator says to me that it's 22.75. Okay, so this is the real true range of uncertainty on the area. It could be as low as 13.75, could be as big as 22.75. I better put it less than equal. And by the way, on the left side is less than or equal to. On the right side is just less than but not equal to. All right, so can you see the problem here? If I report the answer as 18, that gives the entirely wrong idea as to what the range of uncertainty is, right? So how do we deal with this? Well, if you're an engineer, what you're going to do is you're going to report the answer like this. You're going to say that the answer is somewhere in this range, and that is the best way to do it. But it's cumbersome to do it that way. So we're going to go with a simplified version that is actually not rigorously as good as what an engineer would do, but it's a heck of a lot better. So if we have 6 on this side and 3 on this side, what we're going to do is we're going to say, well, the area, we're going to report it as the width times the height. And when we put it in our calculator, we're going to get 18, but we are not going to report it as 18. We're going to use the rules for sig figs, which is an abbreviation of significant figures. And those of you that took Mr. Miller's chemistry class, he assures me that you guys are experts in sig figs. If you haven't yet taken his class, then what we're about to do is new, but it shouldn't be very hard to do. What we do is we take the one number, which is 6, and we look at it and we ask ourselves, how many significant figures does it have? So it only has one sig fig, okay? And then we look at the number 3 and we ask ourselves, how many sig figs does it have? Well, it also only has one sig fig. Okay, so the rule that you should have learned in Mr. Miller's class, and if you didn't, you're learning it now, is that we look at our input numbers, and whichever one has the least number of significant figures, that determines what we can use for our answer. So our calculator said 18, but we can only use one sig fig. So that means we could either round it down to 10, or that's supposed to be a 10. It may not look like a 10, but it's, okay, let's try that again. All right. So we could either round the answer down to 10 or up to 20. So which one is it closer to? Well, 18 is closer to the 20 than it is to the 10, right? So in this class, whenever we're working with measured numbers, 6 times 3 is not 18. In this class, 6 times 3 is 20. Provided we're working with measured numbers. Now, there will be many times in this class where we will be working with defined numbers, exact numbers. So if that's the case, then don't go letting those be the limiting factor. The limiting factor is the measured number that we go with. Okay. All right, so we should play around with the sig figs. We should do a little exercise in sig figs here. That's not the one I wanted. Let's go to this one. All right. So let's do a little practice here. So I want you guys to tell me and type into the chat box here, how many oops, that wasn't the one. Okay, why is it doing this? Okay, here we go. How many significant figures do you guys see in this number right here? Please type it into the chat box. And my chat box got hidden. Sometimes when I share my screen, the chat box gets hidden. Okay, now it's back. So you're saying what number? Can you not see the number? Okay, so it looks like you can all see the number now. Okay, good. All right. All right, looks like everybody's agreeing that it's 3. Well, now let me just play devil's advocate here. So I can see 6 digits there. I see that one, this one, this one, this one, this one. So I see 6, and yet you're claiming that only 3 of those are significant. So I'm guessing that it's the zeros that you think are not significant. Can somebody unmute yourself and explain why are those zeros not significant? Calvin typed it into the chat box. He's saying that those guys are placeholders. He's saying that they don't count, all right? And that is exactly the way that I would word it too. So if I were to look at 2 numbers, one of the numbers is 483, all right? Do you agree that 483 is a very, very different number from 483,000? Yeah, I mean, one is way smaller than the other. So those zeros there, they serve a very important point. They have to be there because if those zeros weren't there, we would have the number 483, which would be way, way, way smaller than the number we want, which is 483,000. So they serve an important function, but they are not actually significant. So if we write the number 483, let's say that that's the area that we calculated, okay? What that means is we are confident that the real true area is somewhere between 482,500 and 483,500, okay? When we write this number, this right here is what it means, okay? They could be anywhere in that range. And so that's why we put the zeros there, and they are not significant. All right, now let's go. What if that comma there wasn't a comma? What if that was a decimal point? Now, let me ask the question again. In fact, tell you what, rather than typing it in the chat box, let's do it a different way. Let's take a poll. That way, I think that would allow me. So I want everybody to answer the question, how many significant figures do you see in this number on your screen? The results are very interesting so far. And they're about what I had expected, which tells me it's a good thing that we're going over this. All right, 2 more people need to respond. 1 more person needs to respond. One person probably can't respond because they're on their phone, not on the computer. All right, so I'll go ahead and end the polling here and share the results. All right, so 7 of you thought that there were only 3 sig figs in this number. 6 of you thought that there were 6, or I'm sorry, 5 of you thought that there were 6 sig figs. Now, those of you that said 1 and 4, I'm not quite sure what you were thinking there. To me, it's either 3 or 6 pretty clearly. If you're one of the people who said that you thought that there were 6 sig figs, could you please unmute yourself and tell me how did you come up with 6?
Because I kind of forgot about the zeros rule, so I just said 6 on accident. I mean 3 on accident.
Oh, so okay. Somebody who said 6 and can tell me why you said 6. Please unmute yourself. I heard somebody trying to talk there, but I couldn't hear what you said. Okay. Will is saying because Miller said so. Okay, well, yeah, you certainly don't want to argue with Miller there. Can anybody think why would Miller say so?
Zeros that come after the decimal count.
Okay, but why? Why do they count? All right, I'll tell you why. All right. So remember what I did a few minutes ago was I wrote the number 483 on my screen there. And I asked you, was that significantly different from the number 483,000? So yes, I mean, 483 is a lot smaller than 483,000. So they are very, very different numbers, very different. Is 483 very, very different from the number 403.000? Hopefully you guys agree that, yeah, it's not really any different. If those zeros weren't there, these two would be exactly the same. So we don't need those zeros there as placeholders. Where up here, when we had a 483,000, okay, those zeros, they were important. If we left those out, we would be in big trouble. In this case down here, we don't really need them as placeholders. And yet we put them there, okay? So if we put them there, we must have had a reason for putting them there. The reason would be that they are significant. All right. So when you see zeros that are on the right side of the decimal point there, they are very definitely significant. All right. So the correct answer for this one is the 6. There are definitely 6 sig figs in this number here. All right. How about this one right here? Let's take the poll again. Let me launch the poll again. Here goes. All right. So again, I want everybody to type into the poll here. How many sig figs do you see there? Okay, this is interesting. I still need 3 more people to, well, actually, I guess 2, because one person can't respond. Okay. All right, here, let me end the polling and share the results so you guys can see. Okay, so almost everybody says 5. One person said 4 and one person said 6. So I'm not sure where you got the 6 from. The 4, I could understand why somebody might theoretically think that it's 4. Okay, so we got a 0 here, and I'm sure that the 0 is the one that causes the confusion. So is that 0 significant? Well, those of you that have taken Mr. Miller's class, no. Yeah, I figured that probably was just somebody clicking on the wrong one. Don't worry about it. That's okay. That's what I assumed it was. All right, so Calvin is saying that middle zeros count, and Calvin is exactly right. So whenever you have a 0 that's in between 2 other numbers, okay, so that 5 is obviously significant, the 6 is obviously significant. So if you ever have a 0 that's in between two significant numbers, okay, that 0 is very definitely going to be significant. So the answer is definitely 5. Okay. All right, let's try another one here. All right, so now, instead of just asking you how many sig figs there are, I'm going to ask you, what is the answer to this question? Now, I don't have this one set up for a poll, so this one you're going to have to type the number into the chat box, okay? I want you to tell me the answer, but I want you to give me the answer using the correct number of significant figures. And by the way, get in the habit of bringing a calculator with you. We are going to be using calculators all the time in this class. All right, so I'm seeing 2 different answers. I'm seeing somebody says 9,000, other people are saying 10,000. It looks like 10,000 is definitely the more popular answer. Okay, so all right, that makes sense. The one who got the 9,000 is saying that they did it in their head. Okay, all right. Let's just make sure that everybody understands how this works, just in case maybe some of the people aren't answering here. All right, so when I type this into my calculator, so I get 29,000, oops, I guess it helps if you turn the calculator on, 29,407 divided by 3. So my calculator is telling me that the answer is 9,802.33333 repeating. All right. And now I need to decide how many significant figures am I going to report my answer with. So I have to look at the numbers I've been given. This number has 5 sig figs. And my other number only has 1 sig fig. And it looks like you guys are pretty much in agreement that the rule says whichever number has the least amount of sig figs, that determines how many sig figs I'm allowed to give in my answer. So my calculator says this, but that's too many sig figs. So I'm only allowed 1 sig fig. So I got 2 chances. I could either round it down to 9,000 or I could round it up to 10,000. Clearly, rounding it up is the more appropriate way to go because the number on my calculator is closer to 10,000 than it is to 9,000. So 10,000 is in fact the right answer. All right, so the rule here that you guys need to get to do is whenever you're multiplying or dividing, you look at the 2 input numbers and whichever number has the least number of sig figs, that's the one that determines how many sig figs you're allowed in your final answer. Okay, what about if you're adding or subtracting? Let me give you one here. What if we do 9.63 plus 4.7? All right. I want you guys to do that one and tell me what the answer is, but report your answer using the correct number of significant figures. And, okay, so I'm seeing one answer. Somebody else? Okay. All right, so I'm seeing 2 different answers here. This is interesting. Okay. So some of you are reporting the answer with 3 sig figs, some with 2 sig figs. One of you reported it with 4 sig figs. All right, so let me do it and let's see what we get. So when I put it in my calculator, or if I do it in my head, so I got 3 comes down here, 6 plus 7 is another 3, carry the 1, so that's 10. So I get 14.33, or at least that's what my calculator gets. Now, the question is, what do I report as my answer? So some of you are going to be tempted to use the same rule for adding that you did for multiplying. Some of you are going to be tempted to look at this number and you're going to say, well, this number only has 2 sig figs. And so you're going to be tempted to say that I need to round my answer to only 2 sig figs. So some of you are going to be tempted to say that the answer is 14. Hopefully the rest of you know that that's wrong, because the rules for sig figs are different when you're adding as when you're subtracting. When you're adding or I'm sorry, so they're different when you're adding or subtracting than they are when you're multiplying. When you're adding or subtracting, what you do is you look at the columns. You see, where does the confidence end? Okay, so if I've got 9.63, that gives me 2 digits after the decimal. And my other number is 4.7. That means I only have 1 digit after the decimal. All right, so my confidence ends after that 1 digit. So I drew a vertical line here. So that shows me where my confidence ends. So this number 4.7, okay, let me erase something here. Just let me erase this. All right. So this 4.7 number is actually 4.7 question mark. All right. So then the question is, what is 3 plus question mark? Well, the answer is not 3. The answer is actually question mark. All right. And then what is 6 plus 7? Okay, that's good. All right. So my confidence goes all the way out to the first digit after the decimal point. My answer then is not going to be 14. My answer is going to be 14.3. That makes sense? Do not use the same rules when you're adding that you do when you're subtracting. Okay. Now, just for grins here, There is a slight complication that we should talk about. Remember how we said that this is 3 plus question mark? So this number here is not really a 3. It could be a 3, but it also might be a 4, could be a 5, could be a 6. We don't really know what that number is. So it's possible that we might round up or we might round down. So here's where it gets a little bit iffy. Some of you might want to round up, but in this case, it's not really clear. So how about if we change the problem a little bit? What if well, let's do 9.67 plus 4.7. Okay, now when we do it, we get a 7. Actually, remember this, that 4.7 is actually 4.7 question mark. Let me switch to yet another color. So that 4.7 is actually 4.7 question mark. Okay. All right, so what is 7 plus question mark? Well, the answer is really question mark, but we know that it's at least 7. All right, so now let's do the rest of them here. So 6 plus 7 is 13, carry the 1. So we get 14.3 before, but it's 14.3 question mark, which we know is at least 7. So if we go rounding this off, we're not going to round down. We're going to have to round up. So the answer is going to be 14.4. All right. Either way, we're going to have 3 significant figures in our number, not 2. Now, whether we round up or whether we round down, okay, that's a little bit of a question mark. In this case over here on the right, clearly we have to round up. This case on the left here, yeah, not so clear. Maybe round up, maybe round down. So what I would recommend is look at the number that your calculator gives you. And so if this first uncertain number is less than 5, I would say round down, even though you could make an argument for that's not really a good thing to do. And it would be an interesting argument to have, but let's just keep things simple. Let's just put it in the calculator and look at the first digit here that's in the uncertain column. And if it's less than 3, we'll round down, even though you could make a good argument for that not being the right thing to do. Let's just simplify it and let's say that's going to be our rule. Okay. Does anybody have any questions about what we've just done there? I'm not seeing any questions, not hearing any questions. All right. In your homework tonight, you're going to have a bunch of problems that when you look at them, you're going to say, wow, these are ridiculously easy questions. All we have to do is multiply 2 numbers or divide 2 numbers or add 2 numbers. Why would Mr. Hendricks assign us a homework problem that's so absurdly easy? Well, I'm not really testing to see if you can add or subtract or multiply or divide. I'm testing to see, can you report the answer using the correct number of significant figures? That's what I'm going to be after. So if you report a number that's right straight off your calculator and you didn't round it off appropriately to the right number of significant figures, you're going to get it wrong. Okay, that's the reason we're doing tonight's homework. All righty, let's talk a little bit more about tonight's homework. Let's go into here. Okay, let me go back. Okay, another thing that you're going to have to be doing in tonight's homework is you're going to have to be converting units. Again, if you took Mr. Miller's chemistry class, you should be an expert in unit conversions. He should have talked about something that we call the Ames method. And there are people at other schools get a little unhappy with us when we call it the Ames method, because people in the other schools say, well, hey, it's the same method we use. All right. Well, we call it the Ames method because we are very particular about how we do this. Like for instance, let's suppose that I give you a number like 2.58 centimeters. And I want you to convert that into meters. Now, hopefully you guys know that there are 100 centimeters in a meter. And so you know that you're either going to multiply by 100 or you're going to divide by 100. And a lot of people, what they do is they say, well, let's try multiplying them and let's see if that number looks reasonable. And if the number doesn't look reasonable, then we'll try dividing, okay? Which is not the way that I recommend you do it. What I recommend is, well, the Ames method requires that you write down the number with the units. And then next to that, you write some parentheses and a horizontal line. And what you're going to put in those parentheses are the conversion factors from above. Okay, so one of these guys is going to go on top and one of them is going on the bottom. The question is, how do you know which one goes where? Well, what you got here is centimeters, and so you want to get rid of the centimeters. You're trying to get the centimeters to cancel out. The only way the centimeters could cancel out is if you put centimeters on the bottom. So that means you've got to put the 100 centimeters on the bottom, and then the thing that 100 centimeters is equal to goes up on top. Okay, and now this next step, this is an important part of the Ames method, and this is the step that a lot of people leave out, so don't go leaving this out. Okay, the next step is we cross out the units. Okay, it's really important you do that because it's so easy to get it wrong. It's so easy to say, okay, I got 2.58 centimeters. And if we're not careful, we can do it this way. Okay, and if we don't cross out the units, we'll never know that it's wrong. But if we do cross out the units, okay, so remember centimeters on top is like one there. So we got centimeters on top, and we say, whoops, well, then we know that we messed up because they're not canceling out the way they're supposed to, right? So now we can know that we did it wrong. So crossing out the units is a very, very important part of the Ames method. All right, so we do that. And so now what we're left with is 2.58 divided by 100. And then the only units that are left now are meters. So we go ahead and write that. And so when we're dividing by 100, we know we move the decimal to the left there. So 0.0258 meters. That's our answer, which I fully recognize that many of you could have done that in your head. And you say, why did I need to write it all out? I mean, I do it in my head. Well, the reason you need to write it out is because we're going to be doing a lot of problems where you won't be able to do it in your head. And if you don't write it out, what's going to happen is you're going to multiply when you should have divided, or you're going to divide when you should have multiplied, and you're going to get the wrong answer. So get in the habit of writing it out, get in the habit of crossing out the units. Okay, so if you do the unit conversions here, and as long as you follow the Ames method, you will be fine. Are there any questions about that before we move on? Not seeing anything, not hearing anything. All right, so let's go back to this. This is a table that you will see in your book. And you need to get familiar with all of these different prefixes. Most people know about centimeters and millimeters and kilometers. Those are ones that you should already be familiar with. Well, get used to these others. So micrometer or micro whatever. It doesn't have to be meter. It could be, in this case, is micrograms, okay? Or it could be microliters, or it could be microamps or microvolts. It could be micro anything, okay? So get used to it. Micro means 1/1,000,000th, okay? And the symbol for it is this little U with an extra tail there. It's the Greek letter mu. So get used to that. Nano is one we're going to be using an awful lot, okay? It's 1/1,000,000th, right? Now, pico and femto, we're not going to be using them hardly at all in this class. Don't worry too much about them. But certainly, and let me clear the screen here. From nano up through giga, we are going to be using these a lot. Everybody needs to know them. Now notice we've got a lowercase n and an uppercase m. Okay, be careful with those. If you see an M, it makes a big difference whether it's lowercase or uppercase. If it's lowercase, that means milli whatever. If it's uppercase, that means giga whatever. I'm sorry, mega. That means mega whatever. Okay. All right. So just get used to these, and you guys will be in good shape. Okay. And let's see, what else did I have in here? Okay, this is from the book. You can see, when you read the book, you're going to see this exact example here. And you'll see that they follow the Ames method. And so the people who write the book, they say, well, you know, that's the method that everybody uses. Well, I've seen a lot of students who don't use this method. So I insist that you do everything that you see here. In order to be the Ames method, you need to have everything. All right, precision versus accuracy. This is a page that's taken from the book. I think we've already talked about that pretty sufficiently. So I'm going to move on. Let's see. So the reason that I put these here was just to kind of illustrate precision. When we draw graphs in physics, we always want to have error bars. In mathematics, you didn't really need the error bars so much, because in mathematics, you were working with exact numbers. But in physics, we are working with measured numbers, and it is always, always important that we make note of what the level of uncertainty is, because that's the only way we can say with certainty whether or not the Earth was flat. Okay, this data point that you saw down here for St. George, if we didn't have those error bars, we would not be able to say with confidence that the Earth wasn't flat. Only when we have the error bars can we say, okay, so the prediction says that it should be up here, the measurement is down here, and even when you take the uncertainty into account, it still does not line up with the numerical prediction. And so now we can say with certainty the Earth is not flat. Had we not included those error bars, we would not have been able to say that. Okay. And let's see, let me go back here. Okay, so in the book there, they're going to talk about graphing data, but I'm going to just skip over that because I think when we did our flat Earth activity, I think we talked about all the important things we need to. Let's see, there's one other thing that I wanted to talk about here. Let me go back to a little bit out of order here. Okay, so here we have 2 pages from the book. In your homework tonight, I am asking you to do problems 1 through 12. And every year at the beginning of the year, I always have people who say, well, Mr. Hendricks is kind of confusing because we have a problem 1 over here that's called example problem 1. And over here, we have another thing that's problem number 1, practice problem number 1. So which one do you want us to do? Well, when you read the book, I would hope it would become evident. This example problem number 1 is one that they have worked through for you. So it's not what I'm going to assign as a homework. The homework is going to be the practice problems. That's what I want you guys to do, okay? And also, every year at the beginning of the year, people say, well, Mr. Hendricks is not clear how I'm going to answer problem number 1 here. Because, let me zoom up. Oh boy, hang on a sec. Okay. What I need to do is I want to zoom up on this problem. There we go. Okay. Okay. When you look at problem number 1 in your homework tonight, you're going to see that they're asking a question about voltage, resistance, and current. Now, those of you that have had my engineering class, you can say, this is easy. We know all about this. This is Ohm's law. Most of you have not had my engineering class. And so you don't know the equation to use, because clearly what's going to happen is we have an equation. And so if you haven't had my engineering class or my electronics class, either one, then you're not going to know what is the right equation to use unless you read the book. If you read the book, it'll tell you. Look here at example problem number 1. All right. They give you the equation here to use. So even if you don't know what a volt is, or what an ampere is, or what an ohm is, you don't need to. They give you the equation right there. So V equals I times R. Even if you don't know what V is, or what I is, or what R is, if they tell you, so they're going to say that the voltage is 120. They're going to say that the current is 0.75. Okay, you see they say it right down here is where they say it. Okay, so even though you don't really know what those words mean, if you know what V is and you know what I is, then you know how to solve for R. Okay, so if V equals IR and you want to solve for R, okay, well, just divide both sides by I. Whatever you do to the right side, you have to do the same thing the left side. So then you're left with R equals V over I. Okay, and so if you know that V is 120 and you know that I is 0.75, you plug it in. Do not forget about sig figs. All right. When you report your answer for R, whatever number you report for R has to have the correct number of sig figs. Remember what I said a few minutes ago about how many of the problems that you're going to work tonight, all you have to do is multiply or divide or add or subtract. And you're going to say, well, this is ridiculously easy. Remember, the real purpose of the homework tonight is to see, can you report the answer using the correct number of significant figures? That's what I'm going to be looking for. Now, I am, of course, also hoping that you can add and subtract and multiply and divide. I'm trusting that at this point in your careers here, you can do that. All right. Okay. So now, with that being said, let's jump down to the very last page. Okay, why does it keep doing that? All right. Okay, here's your homework for tonight, right here. Problems 1 through 12 in chapter 1. And notice what I'm saying here, some very important rules. Okay. You need to show your work. You won't get credit if all you do is show your answers. Okay? Very important. So when you submit your work, don't just write down what the answers are. You need to show me how you got the answers. Okay? Also, remember that if your answer has the wrong number of significant figures, it will be marked wrong. Okay? So there's two ways that you can submit your homework. One is you can just do your work on paper and then submit photographs of it. That is perfectly acceptable. That's one that I found that most students actually prefer that. But if you're one of those people who prefers to type your answers into the Canvas text box, that would be okay. I've given you both methods there. I fully accept either method. All right, well, that's pretty much everything that I have here. Do any of you have any questions about what we've talked about or what the homework is?
I'm going to have a couple problems with this because I can't wrap my head around it.
What is it that's giving you the most problem? Is it the sig figs or?
Yeah,
is it...
the sig figs.
Okay, well, tell you what, stick around after everybody else logs off. Then you and I will talk privately, and I'll even turn off the recording so you don't have to worry about being embarrassed. Unless
right.
you and I talk privately after everybody else signs off. Anybody else have questions about it? In fact, tell you what, I'll turn off the recording so that maybe you're embarrassed to ask because you know it's being recorded.